So let's try one last example of an applied optimization problem. Here we're asked to determine the points on the graph of y equals x squared plus 1 that are closest to the point 0, 2. So I'm going to draw in the graph of y equals x squared plus 2. Sorry, x squared plus 1. And then we've got the point 0, 2. So we're supposed to be finding the point xy, or maybe more than one. There may be more than one point, but we're supposed to be finding points xy on the graph of y equals x squared plus 1 that are closest to 0.2. So I'm just going to put in an arbitrary point with coordinates x and y. Now it could be that the nearest point is this one down here at 0, 1, in which case you would have a single point. But if it's a point other than if this is not the closest point, then the closest point is going to be off the y-axis, and by symmetry there will be two of them. So let's see what happens. Alright, so I don't see the word maximize or minimize. All I see is the word closest. Well, 2 points are closest when their distance is a minimum. So what we want to do is minimize the distance between these 2 points. So this will be our primary equation. So I hope you remember the distance equation. What we need is to take the difference in the y-coordinates, square that, take the difference in the x-coordinates, square that, add those two squares, and take the square root of the result. So we would have y minus 2 squared plus x minus 0 squared. Alright, so if that's our primary equation, and remember the primary equation is the equation for the thing that needs to be maximized or minimized, and we want to minimize the distance, so this is the distance equation is our primary equation. Now it's probably not in its final form, but that's okay for right now. In fact, we know it's not in the final form because we have two different variables here. Well, I'm going to go ahead and expand out what's going on under the radicals. So let's see, the square of y minus 2 would be y squared minus 4y plus 4, and then the square of x minus 0 would be x squared. Okay, so there's our primary equation. We need a constraint. Is there anything that restricts our choice of x and y? The fact that it lies on this parabola is a big constraint. And so our constraint equation would be that y equals x squared plus 1. So what we need to do is then somehow take this and put it in here. Well, we could replace each y with x squared plus 1, but then that would give us x squared plus 1 squared, which would mean an x to the 4th term, and that might be hard to work with. So here is my proposal. Let's solve this equation for x squared. Subtract 1 from each side. Now let's take this and replace the x squared with y minus 1. So what we get is d equals the square root of y squared minus 4y plus 4 plus y minus 1. And that simplifies into the square root of y squared minus 3y plus 3. All right, so let's go ahead and differentiate then. So I'm going to, pardon me, I'm going to rewrite this as y squared minus 3y plus 3 to the 1/2. So d prime is going to be y squared minus 3y plus 3 to the negative 1/2. I left the 1/2 off the beginning. So we took the derivative of the outside function, 1/2, y squared minus 3y plus 3 to the negative 1/2. Now we need to multiply by the derivative of the inside function, and that would be 2y minus 3. And let's rewrite that. The 2, there's going to be a 2 in the denominator. And then there's going to be y squared minus 3y plus 3 to the 1/2. And then there's going to be a 2y minus 3 in the numerator. Alright, so let's look for critical numbers. So I've rewritten the derivative d prime as 2y minus 3 over 2 times the square root of the quantity y squared minus 3y plus 3. Alright, so for critical numbers, we're looking for places where the derivative is either 0 or undefined. Well, where is it 0? Well, it's 0 when the numerator is 0. That's going to give us 3/2. Now, when is it undefined? Well, it's undefined when the denominator is 0. Well, let's see, the only way the denominator can be 0 is if the expression under the radical is 0. So let's see, if y squared minus 3y plus 3 equals 0, that will not factor, so maybe we need to use the quadratic formula. And so by the quadratic formula, we would need negative b, which would be 3 plus or minus the square root of b squared, well, 3 squared, but that negative 3 squared, they're the same, minus 4 times a times c. And I'm going to stop right here because that's going to be 9 minus 12. That's going to be a non-real number, so there are no solutions to that. Alright, so the only critical number we have is y equals 3/2. So two things remain to be done. We need to determine the x-coordinate, and we need to determine that we have actually found a minimum. Alright. So, remember that the relationship between y and x is y equals x squared plus 1. And so if y is 3/2, 3/2 equals x squared plus 1. Subtract 1 from each side. 1/2 equals x squared. So x equals plus or minus the square root of 1/2, which is about 0.707 if I remember correctly. So it looks like we have 2 points. We have plus or minus the square root of 1/2 for x, and for y we have 3/2. Now, let's show that we have a minimum. Well, I don't think I like the idea of using the second derivative test because I don't want to differentiate this. So I think I'm going to use the first derivative test instead. Alright, so let's see. We've got one critical number, which was 3/2. So for our intervals, let's make, say, 0 to 3/2 one of the intervals, and then the other interval is from 3/2 to infinity. And then let's pick a test number from each side. So how about 1 and 2? Alright, so let's try 1 and 2 in d prime. So when y is 1, what is d prime? Well, the numerator is going to be negative. It looks like it'd be 2 minus 3, so that'd be negative. Now, if the denominator is defined, it's going to be positive because of this radical. It's the principal square root. So if we put in a y, we're going to get y, 1 minus 3 is negative 2 plus 3 is 1. So we're going to get 2 in the denominator and negative 1 in the numerator. Yeah, that's negative 1/2. So d prime is negative. That's good because that means d is decreasing, which is good if we want a minimum at 3/2. So let's try 2. Well, the numerator is going to be 2 times 2 minus 3. That's 1. That's positive. That's good. Because, again, the denominator, if it's defined, is going to be positive. So let's put in the 2. So let's see. 2 squared is 4 minus 6 plus 3. That sounds like 1. So it looks like we're going to get a positive number in the denominator and a positive number in the numerator. Excellent. The derivative is positive on the right side of 2, so that means the function is increasing. So the function decreased and then increased. We have a minimum at y equals 3/2, and that is all courtesy of the first derivative test.